Hello friends, welcome back to the series on physics of solids. In the last episode, I introduced the topic of X-ray diffraction, and we already talked about the importance of X-ray diffraction in the whole story of deriving the structure of ordered crystalline structures. So there, in addition, we saw some basic concepts concerning XRD. In this episode, we will continue our discussion on XRD into more advanced topics. Basically, the plan is to look more into experimental details needed while you do a diffraction experiment and analyze the XRD data. So let's try to do a short journey into such kind of informations. So, the first and foremost question in that kind of an exploration would be, what are the fields in which the XRD can be applied? What are the what are the kinds of applications of an XRD study? First and foremost, it is about the characterization of crystalline materials. So, what all does the characterization include? It is about the quantitative determination of crystallinity, which is very important. So, crystallinity, how much is the crystalline contribution in a whole sample, which is a very important parameter for determining which will predict the properties of many materials. I already touched upon the importance of crystallinity versus amorphousness, right. So, that is one thing which is very well can be estimated based on the intensities of an XRD spectrum. Second, determination of the unit cell parameters or unit cell dimensions, which means that A, B, C values of the unit cell, which means that which will extend you to get the dimensions of the Brillouin zone, which we discussed in one of our earlier lectures, right. And the third point would be the measurement of sample purity. The purity of the sample is very important for any kind of sensible application. You should have an estimate of the purity of a sample to the fractional digits, which is desirable for a particular application, whatever be the application it be. So, there are various techniques for measuring or estimating the purity of a sample. XRD is one of them, but one should be cautioned that XRD is not the ultimate technique to measure the sample purity. There are other techniques like atomic absorption spectroscopy or ICP-AS, atomic emission spectroscopy. So, there are other techniques which are available for the estimation of the sample purity, but the beauty of the XRD technique is that in all other techniques you will be changing the physical characteristics of the sample while you estimate the purity of a sample. Whereas in XRD, you will be maintaining the same physical features of a sample, and at the same time you will be estimating the sample purity, which is very important for an engineer's point of view whenever he adopts a sample or a solid for any kind of practical applications. And again, there are other competitors for the XRD in this field also, which I am not touching upon, but in any case XRD would be the initial point of contact for such an estimation. And the fourth point would be the identification of fine grained minerals. So, because the minerals are very much being explored with the help of XRD, because as you know, the minerals are mainly made up of high atomic number elements. So, naturally XRD would be very much applicable, and then it will have multiple constituents from different kinds of crystals in a mineral, which in an XRD you will be able to clearly distinguish between different sets of crystalline groups in a mineral. In many XRD, to start with, you may be concerned only with one class of crystals. You must have studied about the point groups in space groups. or the space groups. There you know that there are different space groups, and that is what characterizes a crystal. But in a mineral there will be different kinds of crystals which belongs to different space groups contributed by different atomic constituents, and XRD can very well clearly distinguish between these different constituents. And the fifth option or the application would be structural stability with external parameters. So, how to do it? You can always perform the X-ray diffraction experiment while changing the external parameters such as say temperature or in presence of some kind of a chemical or so pressure. In all these presence, you can definitely repeat your X-ray diffraction experiment and see the structural stability studies. And again, so that is the preliminary kind of applications of the XRD, but this application can be extended or widened with the help of other techniques. For example, with the Ritweil refinement, one of the refinement techniques with which you find out the crystal structure and the strain of the compounds, you would be able to extend the applications of XRD. So, you must have heard about the thin film samples, where we are essentially talking about two-dimensional materials coated in a two-dimensional manner, which are very thin films. The films will be of the order of say angstroms or nanometers or micrometer. So, these thin film samples can be characterized based on its stress, strain, roughness, thickness, density, dislocation density, and then estimation of the superlattice and a whole lot of parameters. So, for the whole semiconductor industry, the XRD techniques is very important, because they basically use in the semiconductor industry, we basically use the thin film samples for our kind of applications, and correct estimation to the many fractional digits is very important. Correct estimation of the strain, the stress, and a whole lot of parameters is very important for adopting any sample for technical application in a semiconductor industry. Now, X-ray diffraction. So, you know that there is the X-ray, and the X-ray is getting diffracted from the crystal. So, based on that itself, I can list now itself 5 different techniques in which we use the basic technique of XRD and try to derive different kinds of information. For example, let me list it. First, X-ray powder diffraction. Second, single crystal XRD diffraction, grazing incident angle diffraction, X-ray reflectivity, and small angle X-ray scattering. I am not detailing all the 5, but for a preliminary study, the first and foremost and the most widely used technique for the XRD is X-ray powder diffraction. So, now the question is that what is an X-ray powder diffraction means by? The X-ray powder diffraction is more aptly named polycrystalline diffraction. So, the word itself will tell you that there are different kinds of crystallites in a single group of sample which you use. So, how is those polycrystallites differ? Those crystallites do differ in terms of the kind of parallel planes which are present in those crystallites. But there should not be any confusion about the term powder. The samples can be powder, it can be cindered pellets, which means the pellets which are being hot pressed and which has been passed through a procedure of heating and making it stronger, that is a cindered pellets. So, samples can be powder, cindered pellets, it can be coatings, thin film coatings, on substrates or thin films, etc. So, powder diffraction, X-ray powder diffraction need not necessarily be on a powder kind of sample, it can be on all those things. So, what is the opposite of the powder diffraction? The opposite of powder diffraction is single crystal XRD, where you have got only one class of crystallites in a sample, or you are focusing only in one single set of parallel planes. So, that is a single crystal XRD. The ideal powder sample contains tens of thousands of randomly oriented crystallites. So, that is the criterion for deciding if the sample is of a powder or not. It should have tens of thousands of randomly oriented crystallites. Every diffraction peak is the product of X-rays scattering from an equal number of crystallites. So, how do you ensure that it should be equal number? So, while doing the experiment itself, you will make sure that the crystallites are randomly distributed into the area of focus into which the XRD really strikes the sample. But we should always remember one point: only a small fraction of the crystallites which can produce coherent diffraction with the X-ray radiated at a particular angle in the specimen actually contribute to the measured diffraction pattern. So, therefore, what is the way out for getting a better intensity or better resolution in your or a signal to noise ratio in your XRD? The answer is very simple: irradiate a larger area, right? You have to make sure that your XRD incoming radiation is of enough width so that you get a better signal to noise ratio. So, irradiating a large volume of material can help ensure that a statistically relevant number of grains contribute to the diffraction pattern. Now, let us look how a powder diffraction pattern works with the help of this cartoon. Now, imagine that I am taking a group of crystallites or a powder sample randomly distributed on the focus of X-ray. So, I put an X-ray radiation into the crystallites. Now, the X-ray diffraction, in the X-ray diffraction, the X-ray radiation will produce a coherent interference with those planes which have got a favorable angle of incidence with the X-ray radiation, right. Now, as you can see in that cartoon there, the blue, which I have colored it as the blue crystallites, are actually those which has produced a diffraction at an angle 2 theta. So, we have already seen the formula of which governs the whole X-ray powder diffraction. What is that rule? That is the Bragg's law, which is n lambda is equal to 2d sin theta. So, what are the contributions in there? You have the lambda, you have the d and the theta, right. So, where the theta is the Bragg angle. So, provided that your incident X-ray radiation is of a constant wavelength, which means that the theta is going to be decided by the d, the distance between the planes. So, taking that point into consideration, the blue point, so the radiations which are diffracted from the blue lines and which will be recorded at an angle 2 theta will have contribution from those set of crystallites having parallel planes which is at an angle of d. But having fixed the incoming radiation of the incoming source radiation at a particular angle itself, you will see that there are other crystallites also getting into picture. For example, in the blue in the cartoon, the crystallites which are marked blue will also have different set of planes. Like if you remember, in one of the earlier lectures I showed you the simple crystal lattices. There you are having 100, 111, 110 in the same crystal. So, XRD will randomly choose all those things, all those planes, and will get diffracted continuously, but the intensities of those diffraction angles will differ. So, whenever the intensity gets prominent, for example, the ones which I have marked in the orange in the cartoon, the kind of crystallites which are marked in the orange color, those crystallites will get a higher intensity at a different angle of the incidence. So, those crystallites will produce a diffraction at a different angle, which means that in the XRD spectrum, the Y versus X spectrum which we get, those yellow crystallites will be producing their peak at a different 2 theta angle. But so that was the basic cartoon to understand how does an XRD spectrum, a powder XRD spectrum works. But for a practical purposes, there are various other geometries being proposed. The most important of them is the Bragg-Bandano geometry or Bragg-Bandano geometry, and within them we call it the theta 2 theta configuration. So, here in the theta 2 theta configuration, both the input radiation, which is the X-ray, and then the diffracted beam is the diffracted beam or the detector which will detect the diffracted beam, both of them rotates simultaneously. So, the source also rotates and the detector will also simultaneously rotate. So, this concept can be very clearly seen in the image there. So, you have the theta and the 2 theta, which is clearly understood from that angle. So, and then the XRD spectrum will come as the function of the 2 theta or the Bragg angle. So, this image shows the Bragg-Bandano diffractometer. This I have taken from the website of Panalytical, which is a leading manufacturer of the diffractometer. There are a lot of other manufacturers also. They will also have something similar, but slightly different in terms of their configurations. There you can see that there are a set of optical provisions, optical inclusions within a XRD technique, which are very compulsory, which we will be seeing in a short while. Among them, the source is the important. So, how does a XRD X-ray source will behave? There are different kinds of sources available in the market, and one has to choose the source based on the kind of application we use. And how does these kind of X-ray sources differ? They differ in terms of their wavelength. As you can see in the image, I have shown 5 different sets of XRD sources available. Molybdenum, which is at a lambda of 0.71 angstroms, copper 1.54 angstroms. Copper is the most widely used X-ray source. And then we have the cobalt, which is 1.79 angstroms, iron, which is 1.94, and chromium 2.29. So, depending on the kind of application which we use, we will be varying. We can vary the tube also. So, how does a X-ray tube work? So, X-ray tube work based on is basically a cathodic radiation. So, there is a high voltage, and this high voltage will start producing will start accelerating the electrons, and electrons start striking a target. A target is target is made of materials which we listed upon, the 5 different source materials which we listed upon. So, these electrons strike against the source, against the target, and this target will release X-rays. Okay. So, these X-rays will be mainly the radiations which coming out is termed by a German term Bremsstrahlung. So, Bremsstrahlung is a German word meaning breaking radiation. So, it is the radiation given off by a charged particle, say for example, in our case the electron. The electron is the one which strikes, right. So, it is a radiation given off by a charged particle due to its acceleration caused by an electric field of another charged particle. Because when the electrons strike against your target material, for example copper, it will have other kind of charged particles. For example, in the copper you will have the nucleus and its constituents, right. So, this kind of the other set of charged particles can create changes in the electron. So, many times it is the acceleration or deceleration, whatever it is. So, but in any case the radiation which is originating out of this kind of acceleration or the deceleration is generally termed by the term is called the Bremsstrahlung radiation, right. So, mainly it will be Bremsstrahlung radiation. So, as you can see there in the figure, a typical spectrum or the radiation coming out of a X-ray tube will have a background of a Bremsstrahlung, but it will have few characteristic peaks. So, these characteristic peaks, depending on the energy gaps or the energy levels between which the transition is happening, there are mainly 2 different kinds of radiations peaks, which is the K alpha radiation and K beta radiations. So, for our experiments, XRD experiments, we generally use K alpha lines or more specifically K alpha 1 kind of lines, which means that the necessary task would be to remove the unnecessary peaks. For example, you have to remove the K beta lines, which means that you do not want many radiations of different frequencies striking against your crystal and diffracting at different angles. So, you need only one single line of a predictable frequency striking against your crystal, which means that your duty is to discard or cut away all the other unnecessary radiations. So, first task is to cut away the K beta radiations. As you see the table there are very specific K beta radiation, K beta filters as it is called for specific tubes. For example, in the copper tube we use a nickel K beta filter. So, with the help of these filters we cut away the K beta, and then there will be K alpha 1 and the K alpha 2, and K alpha 1 we need only K alpha 1, and the K alpha 2 most part of it is cut down with the help of some kind of blocking mechanism which we apply externally, and also the modern spectrometers are having again a software correction to cut away the K alpha 2. In any case, you will be clearly able to understand and to distinguish between it may be in the XRD spectrum, it may be very closely spaced lines, but you will be able to tell that one is K alpha 1 and another is the contribution from K alpha 2, and we normally neglect the K alpha 2 contribution and take only K alpha 1 spectrum or the peak into consideration when we make any kind of sensible analysis of the X-ray spectrum. Now, one has to choose an appropriate incident and detector optics while we work on the X-ray spectrum. Let me list out few of them. One is the divergent slit, then there is the solar slit, then we have the monochromator. I already told about the K beta filter, and then there will be a solar slit in the receiving side also, and then there is a receiving slit and the detector. So, in the figure shows the configuration of all those kinds of needed parts in the needed accessories in a XRD spectrum. Now, having said this much about the powder diffraction, let me put in few sentences about the sample preparation for an XRD spectrum. An ideal powder spectrum, as I told you, powder sample should have many crystallites in random orientations. The distribution of orientation should be smooth and equally distributed among all orientations. So, how do you ensure that? So, when you prepare a sample for the powder diffraction, you should always mention them and make sure that you are not applying any force while you distribute the powder over your the focal plane of the X-ray incident radiations. So, that will ensure a random orientation of crystallites which are having different kinds of planes and particle sizes basically. And when coming to size, crystallites in general should be less than 10 micrometer. Let it be any crystallite, it should be less than 10 micrometer on an average in size to get a good powder statistics. So, as shown, a typical XRD spectrum will have three different contributions. First and foremost, the signal. Signal is what we need for a sensible estimation of what is the XRD about. So, a signal is the most important part. And second is the background. You cannot avoid a background because there are many contributions. There are many constituents which can contribute to a background. For example, if your sample is hygroscopic or as a water absorbing sample, the water itself will be an amorphous contribution in your sample, and that can lead into a big background. And then there is the noise component, which is creating all those vibrations in your spectrum. But in the modern spectrometer, there are softwares available in order to manage all those background noise signals and all those things and make a sensible signal out of that. So, having got this spectrum, your next task should be to assign appropriate Miller indices for that. So, that completes a quick estimation of your XRD, quick study on your XRD spectrum. So, that completes our discussion on the XRD spectrum, and more specifically we talked about the nuances involved in while you are doing a preliminary experiment with XRD with the X-ray diffraction, which is the X-ray powder diffraction. So, the X-ray powder diffraction would be a stepping stone to explore the different possibilities within a crystal, and I encourage all the students to invoke into such kind of topics also. Thanks again for your kind attention. See you next time.